We're starting sections 4.1 and 7.5 with a review of inverse functions before we move into a review of trig functions. I'm going to break this up into two different videos, one on a review of inverse functions and then one on just inverse trig functions. So this is section 4.1, and let's talk about inverse functions. So we have a special kind of function, special classification function called a one-to-one function. One-to-one functions can be identified both analytically and graphically. Analytically, when we are looking at a one-to-one function, it means that if any two different inputs in the domain correspond to two different outputs, then the range of f, then they are called one-to-one. Which means if I have x equals a and x equals b, two distinct values in the domain of f, then f is one-to-one if and only if their outputs are distinct, meaning f of a does not equal f of b. So in simplest terms, we often say then that a function is one-to-one if every x has one y and every y has one x. And then graphically, we remind ourselves that a function is called one-to-one if it passes the horizontal line test. And we say that a function then has an inverse if it is one-to-one. So for example, we want to determine whether this function is one-to-one. So for the following function, the domain represents the ages of 5 males and the range represents their HDL, which is their good cholesterol scores in milligrams per deciliter. So notice we have a domain, right? A domain here that is ages, and we have a range that is HDL values. And you can probably tell that there's going to be a problem because we have 5 inputs for 4 outputs. So we have more inputs than we do outputs, which means that something is going to double up. So if we look at what we have here, we can see that each arrow goes to one value until we find here, this one goes up here. Oh, but here's the problem. 53 also goes to 35. So 41 and 53 are distinct inputs, but they have the same output. So while this is a function, it is not a one-to-one function. So we would say since 41 and 52 have the same output, this function is not one-to-one. It's not one-to-one. So we could also say that for x equaling 41 and x equaling 52, f of 41 equals f of 52. And that's another reason why we could say, therefore, it is not one-to-one. So remember, it is still a function because every input has only one output. But you're not allowed to repeat outputs for different inputs if you want it to be one-to-one and have an inverse. Graphically, remember we have the horizontal line test. So if that's the case, then when I draw a horizontal line through each of these graphs, it should only pass through the graph once. So let's look at the first one, this cubic. Passes through once, passes through once. And while it may look like there is an issue here in the middle, right here in the middle, it is only momentarily tangent. And so if we were to go and zoom way in, we would notice it actually does not get horizontal, so we're okay. But if we look at the second one, we can see that there's a problem because we pass through twice. So this one is not one-to-one. Oops, forgot to mark that the blue one is one-to-one. And how about the last one? Well, let's check. It looks like it's a line, so everywhere I could draw A horizontal line only passes through once, so this one is indeed 1 to 1. And you'll find that all linear functions are 1 to 1 as long as they're not horizontal. So what then is an inverse function? So I've talked about a function having the ability to have an inverse. So it has a property that says it's 1 to 1, which means it can have an inverse. But what exactly is an inverse? An inverse function is a function that sort of undoes the function. What do we mean by that? Undoes is not exactly mathematically what you would expect. So the symbol f, it looks like it's to the power of -1, means f inverse, and it's used to denote the inverse function of f. So in other words, if y equals f of x, and that function is 1 to 1, then f has an inverse function, which is denoted as f inverse. And we usually would say then x is equal to f inverse of y. So for example, what are functions that undo one another? So if I have f of x equals x squared, then f inverse is the square root of x. But bear in mind that that means that x also has to be greater than or equal to 0, because you can't take the square root of a negative number. If I have f of x equals x cubed, then its inverse would be the cubed root of x. So undoing what's been done to x. If f of x equals 2x, the way I undo multiplication by 2 is to do division by 2, so its inverse would be 1/2 x. And we can confirm that two functions are inverses by finding the composition of functions f of f inverse of x equaling x, and f inverse of f of x equaling x. And yes, both of them have to be true in order for it to have a function, or sorry, in order for a function to have an inverse. So both, it is an and, both of these have to be true. So if we want to check that two functions are inverses, we have to find f of f inverse and f inverse of f. And that's the easiest way to do our operations to figure out if two different functions are inverses. So let's do that. Let's look at some examples of functions and see if they are inverses. First one says I have f of x is -3x plus 12 and g of x is -1/3 x minus 12. On the surface, it seems like I went ahead and multiply by -3, so let's divide by -3. I added 12, so now I've subtracted 12. Let's see if these truly are inverses. So let's find f of g, right? F of g of x, which would be f of -1/3 x minus 12, or a -3 times -1/3 x minus 12 plus 12. So we end up with x plus 36 plus 12, which is x plus 48. That does not equal x, so they are not inverses. It's as simple as that. Try again with 3x plus 9 and 1/3 x minus 3. Maybe now we figured out what it means to have a number added or subtracted, and let's see if it works out. So let's find f of g. So f of g of x then would be 3 times 1/3 x minus 3 plus 9. And we end up with, what is that? X minus 9 plus 9, which is just x. Half of the definition is satisfied. F of g of x, in this case, is x. Now let's find g of f. Make it a little neater here. G of f of x. In that case, I get 1/3 and then 3x plus 9 minus 3. So we get x plus 3 minus 3, which is x. Both are satisfied, so these are inverses, which means that f of x, if f of x is 3x plus 9, that means f inverse of x is g of x, which is 1/3 x minus 3. And we could also say if g of x is 1/3 x minus 3, then g inverse of x would be the 3x plus 9. So kind of cool how that all works out. So let's try one last one. Maybe pause here, See if you can figure this one out on your own and see if these two really are inverses. And then come back. Hopefully you took a moment to try. So we've got f of x is x squared, and f inverse is the square root of x when x is positive, or 0. So let's find f of f inverse here. Well, that would mean that in f we plug in what f inverse is. So we would have the square root of x, and we would square it, which is indeed x. And f inverse of f would be the square root of whatever f is, which is x squared, which would be x. So these are indeed inverses. And in the next video, we'll tie together what this means about inverse trig functions. In this example, we want to find the inverse of the following function. This function is one-to-one. We have this set of points, -3, -15, -2, -10, -1, -5, 0, 0, 1, 5, 2, 10, and 3, 15. We want to state the domain and range of both the function and its inverse. So our domain, remember, is a set of x values for which the function is defined. So the domain of our function then is just the set of x values, which are -3, -2, -1, 0, 1, 2, and 3. And the range of our function then is just the set of corresponding y values, -15, -10, -5, 0, 5, 10, and 15. And the interesting thing about inverses are that if they're undoing x by doing the same operations to it they gave it to y, which means going the opposite direction, whatever operations we do to y should give us back x. So operations on x give us y, operations on y give us x. It sounds like what's happening is we are inverting them. Maybe this is where the name inverse comes from. We're going to invert the x and y values. Essentially, graphically, this is a reflection over the line y equals x. So in that case, then what we would know then is that the domain of our inverse function then is the range of the original function. So it's -15, -10, -5, 0, 5, 10, and 15. And then the range of our inverse function then is the set of points that was in the domain. So whatever the domain was, so now it's -3, -2, -1, 0, 1, 2, and 3. So what was the domain of f is now the range of f inverse. And what was the range of f is now the domain of f inverse. And graphically, I guess more abstractly, I've got an idea over here. If I take the domain of f and I send values over to the range of f, that is my function f. If instead I take values in the range of f and send them back to the domain of f, that is our inverse function, which means that the range of f is now the domain of f inverse, and the domain of f is now the range of f inverse. So how can this help us when we're graphically trying to determine inverses? Well, if we were to look at a graph of a function and its inverse, we would notice that it indeed does look like it was reflected over the line y equals x, which is what we have here. So here's our line y equals x. And notice the red and the blue are mirror images across that line. So if I had the points a1, b1, a2, b2, and a3, b3 on the original function, its inverse then takes each of those and reverses them, inverts them. The x becomes the y becomes the x. So now we have b1, a1, b2, a2, and b3, a3. So can this help us graph inverse functions? Absolutely. That's our last example we're going to look at in our review of inverses. I have the function who has 3 points on its graph, which are -2, 4, -1/2, 2, and 3, 3. So if we look at our function f of x, we have the points -2, 4, -1/2, 2, and 3, 3. And what we want to do then is graph the inverse, so f inverse of x, which means we need to invert the order, which means negative 2, 4 becomes 4, negative 2, negative 1 half 2 becomes 2, negative 1 half, and 3, 3, well, it remains 3, 3. And what we want to do when we're trying to graph an inverse is try to follow the points in the same order. So if I had negative 2, 4, I have 4, negative 2. And that one is connected to 2, negative 1 half. So those guys are connected. And then that is connected to 3, 3. So there is our inverse function. And if we were to draw a dotted line through y equals x, we would see where it was reflected across. And it looks like we have a mirror image on both sides. So that is our y equals x line that we went ahead and reflected across, and this would be f inverse of x with the points 4, negative 2, 2, negative 1 half, and 3, 3. So from here, we'll move into inverses of trig functions.